Hello, and welcome to the Sentinel Innovation and Methods Seminar Series. My name is Rishi Desai. I'm an assistant professor at the Division of Pharmacoepidemiology at Brigham and Women's Hospital and Harvard Medical School, and I will be moderating today's session. The FDA Sentinel system helps address questions related to safety and effectiveness of marketed medical products. Innovation Center focuses on developing innovative methods by leveraging new tools, data sources, and enhancing real-world evidence capabilities through advanced analytics. Sentinel Operations Centers focuses on supporting the FDA in use of Sentinel Common Data Model and associated modular programs. Sentinel Operations Center also maintains the FDA's Active Risk Identification and Analysis, or ARIA system. We launched this webinar series to engage experts and innovators in key areas related to the Innovation Center's master plan and Operations Center's methods work. With that, I am very pleased to announce today's speaker, Dr. Ehsan Karim. Dr. Karim is an assistant professor in health data science in the School of Population and Public Health at the University of British Columbia in Vancouver. He is also a scientist at the Center of Health Evaluation and Outcome Sciences at the Providence Healthcare and Michael Smith Foundation for Health Research Scholar. His current program of research focuses on developing causal inference and pharmacoepidemiologic methods and applications of data science approaches in the large healthcare data analysis context. The title of today's presentation is Can we train machine learning methods to outperform high-dimensional propensity score algorithm? This presentation is uniquely suited to the folks who are interested in the Sentinel program, because we are always interested in leveraging newer methods to do better job of causal inference or improving confounding adjustment. So we are very excited to welcome Ehsan and learn from his experience. Before we get started, I would like to mention that your lines are muted. If you want to pose a question, please type it in the Zoom question and answer feature. We will answer question at the end of the session. Finally, this session is also being recorded and will be made available through our website, which can be found at sentinelinitiative.org. Without further ado, I will hand it over to Ehsan and would love to have an active conversation. So please feel free to post your questions in the chat box. Ehsan, take it away.
Yeah, thanks, Dr. Rishi Desai, for inviting me to give this presentation. So this is a work that I have done during my postdoctoral research when I was working at Synods as well as at the McGill University during my postdoctoral research. So here is the title, as Dr. Rishi has mentioned. The title is, Can we train machine learning methods to outperform the high dimensional propensity score algorithm? And here is the outline of today's talk. Before I begin, if you want to follow along with the slides, you can simply go to tinyurl.com/hdPS2022 to get the exact same version of the slide. And here is the outline. At first, I will talk about the basic terminology of high dimensional propensity score algorithm. And then I will spend majority of the time to talk about some of the machine learning alternatives to high dimensional propensity score algorithm that we have assessed in this epidemiology paper that was published in 2018. And that was a joint work with Menglang Peng and Robert Platt. Both of them are from the McGill University. I will talk about the general ideas of the and the principles that we followed to follow these machine learning algorithms. And at the end, if we have some time, I will also talk about some of the related research. Some of them were published after 2018, and I will just try to give a general sense of where this research is going and some of the future directions. Of course, this list will not be exhaustive, but some of these papers are some papers that I found to be related and important as well. All right, so let me talk about high dimensional propensity score algorithm. And to give a general idea, let me start with a motivating example. And this is an example that was published by one of my students, Dr. Basham. in the e-clinical medicine, where he was interested in the respiratory tuberculosis and the association of that with the airway disease, where the respiratory tuberculosis was the exposure variable and the airway disease was the outcome variable. And he was conducting this research using the health care claims data for immigrants in the British Columbia. And the reason why we generally want to use these healthcare claims databases is that obviously we are dealing with a province-wide data source, and we can have large sample size, many diverse population can be included, longitudinal information are available, and we, Dr. Basham did include a lot of linked data sources that were federal and provincial into the medical data sources to get some of the co-readers. But the downside is these administrative data sources are not necessarily designed for any particular research purpose. And we do rely on data sparsity. That means that patients need to interact with the healthcare system for us to be able to get any kind of measurement. So the long story short is that we may not have all of the confounders. Going back to the motivational example, you can see we did have many of these confounders in the health admin data, but we did not have access to the smoking information in that particular paper. So this could be a reason for us to think about what could be a reasonable alternative so that we can reduce this residual confounding due to this unmeasured confounder. And going back to some of these papers, say for example, the paper by Vanderwille in 2019, he gave a very nice description of the modified disjunctive cause criteria that talks about what are the variables that we should empirically adjust to reduce confounding, right? So obviously we should adjust for the causes of exposure, causes of outcome, or both. If we know that we have an instrumental variable, we should not include that. And if we have good proxies of the unmeasured confounding, that should be included in the analysis. So for example, if smoking variable is something that is not available, we should look for good proxies. So for example, we had access to tobacco use in Dr. Basham's research, and that could be used as a proxy variable, right? So the idea of using proxy variables to reduce the unmeasured confounding bias is not necessarily a new one, but within the high dimensional propensity score framework that was proposed by Schneeweiss and colleagues, that was innovative in the sense that that talked about a very general framework under which from the health admin data sources, we can try to identify potential confounders or the underlying confounders that may be associated with general health-related questions that we ask within the health admin data sources. Say, for example, in this particular table, and from this paper of Schneeweiss in 2018, I generally like this table because that gives a very good understanding to the audience members that what kind of variables we are really talking about. So say, for example, in a regular epidemiologic study, obviously we have a lot of codes from the diagnostic codes or procedure codes like ICD-9-10 codes that are available, and we create the variables that are necessary for our data using those codes. We can use the outcome, use these codes to create our outcome data, our exposure data, as well as many of the investigator-specific confounders. But we generally leave out a lot of additional codes that are available in the data sources, but we do not necessarily know how to interpret them, so we do not really touch them, generally speaking. But what Schneeweiss proposed in his high dimensional propensity score algorithm is that even though we do not necessarily know how to interpret some of those codes that we have in our data sources, those information might still be useful. So for example, if someone is coming with a code for use of oxygen canister, obviously that person has a very frail health. That means that whatever outcome that we are using in our research, this particular type of information might also be useful for us to understand the health status of that person. If this person is coming with a lot of codes for the specialist and hospitalization, that might give us some understanding of the chronic sickness situation for that particular patient. So all of this information that we're not generally using in regular epidemiologic study could be useful for our purposes as well. And that was the basic innovation for the high dimensional propensity score algorithm. And they are basically advocating for adjusting for something that may not be directly interpretable within the context of the research question that we are asking, but they do have some useful information, and we are trying to use this framework to find a way to use those information in our analysis. Obviously, the general idea is that these information is coming from the same data sources, so they are correlated, so should be useful as a proxy information. And this idea basically blew up. You can see the paper was published in 2009, and over the years, this is getting more and more citation, even this year. All right, so just to give a very quick understanding of what we are talking about and the design of the study, let us talk about some of the details of the empirical analysis that we have done in our 2018 paper. We were using a clinical practice research data link from UK, and we were basically interested about a post-myocardial infarction statin use as the exposure variable, and the outcome variable was mortality. It was a core study, so we had a cohort entry, and there was an event at the end, and there was a follow-up during which we were observing the outcomes. But the most important part is the covariate assessment window. This covariate assessment window was happening before the cohort entry. That means this is a pre-treatment stage. And at that stage, it could be a 6-month or a 1-year period. And within those periods, we were collecting all of these codes. And where did we get all of these codes? So in the CPRD data, we got the codes from 4 data dimensions. The first one was general practice data. The second one was diagnostic data, procedure data, and medication data. What we have done is that from those data dimensions, we collected the number of various columns from those data sources to get the proxy information or the codes that we have in those data sources. And say, for example, from the general practice data, we had 686 columns. And then what we have done is that we have converted each of these columns to 3 binary variables. And we have converted those based on the intensity of the prevalence. Say, for example, whether they occurred once, or they were occurring sporadically, or they were occurring frequently. And based on that, we basically converted each of these columns into 3 binary variables, and that resulted in thousands of binary codes. So to show you what it looks like in the analysis stage, so you can basically see we had 4 data dimensions. So for example, this is the general practice data dimension, this is the diagnostic, this is the procedure and medication dimensions, and each of these dimensions was associated with many columns, and for each of these columns we were having 3 binary variables. And I will talk about a bit later why we are converting these to binary variables. But the general idea from here is that from all of these columns, we are essentially getting more than 4,000 covariates. And we basically call these covariates as empirical covariates to distinguish them from the investigator-specified covariates, right? So this empirical covariate is an important terminology that I will be using throughout this presentation. So we had basically these binary covariates, basically more than 4,000 binary empirical covariates, but it is too much. So we obviously, if the prevalence is too low, if we are dealing with a 0 frequency or 0 variability in some of these codes, that would create some problem. So one of the things that was proposed in the original algorithm is that we have to use the 200 most prevalent cohorts, and that reduced it down to 2,400 empirical covariates. Obviously, there are some debate about whether we should reduce to only 200 most prevalent cohorts in the literature. But for the simplicity for our presentation today, let's just say that we have these 2,400 empirical covariates based on this 200 most prevalent cohorts. All right, the problem with including this 2,400 empirical covariates in the propensity score analysis is that we may have an overfit problem. But before going to that, let me talk about what is the propensity score model that we are building using this empirical covariates. So obviously we are including all of these 2,400 empirical covariates. Then we have the potential confounder and the important covariates that were identified by the investigators. So since we are without any sorting, we are including all of this information in our propensity score model. We are naming this the kitchen sink model. And when we use this kitchen sink model, look at what is happening to our propensity score distribution when we divide them by the exposure group. So this is the propensity score distribution when we used only the investigator specified covariates. That means the important and the potential confounder covariates, we had 29 of them. And then there was some overlap here. But when we have included all of these 2,400 empirical covariates in our propensity score model building, there was almost no overlap. And whoever has done any propensity score analysis knows that without any common support or overlap, the ultimate propensities, the treatment effect that we will arrive will be very hard to interpret because there is almost no overlap. So there is no counterfactual basically, right? So to deal with this problem, obviously we need to think about a sorting solution, like how do we sort which variables are important to include in our propensity score. Obviously, as we have showed in the previous slide, we cannot include all of these 2,400 empirical covariates. So how do we sort? To solve this problem, the core of this high dimensional propensity score framework is the Bros formula. And Bros formula is something that was proposed in 1966, and that was a very simplified formula where you need to have a binary unmeasured confounder, binary outcome variable, and a binary exposure variable. If you have all of that, you need to simply assume 4 quantities. And these assumptions are for prevalence of unmeasured confounder among the treated, among the untreated, among the dead, among the alive. And if you can assume these 4 quantities, you can just plug in these 4 quantities into this formula. And what this formula does is it gives you the amount of bias due to this unmeasured confounder. So for example, if smoking status was your unmeasured confounder, you simply assume the prevalence of these prevalence of smoking among the treated, among untreated, among dead and alive, and you can probably get that information from the literature if such information was available, right? But when we have the empirical covariates, even though we do not necessarily know the direct implication of those covariates in the research question of our interest, we can simply plug in those empirical covariates to find out what are the prevalences of one particular empirical covariate among the treated, untreated, dead, and alive. And the nice thing about this is that you do not need to assume anymore. You can simply calculate because these empirical covariates are something that you already have in your data sources, right? So what we are basically doing here, we are using this Bros formula and each of these empirical covariates to calculate how much the amount of bias due to each of these empirical covariates, right? So obviously we had 2,400 empirical covariates, and we can simply use the Bros formula. And here I'm basically taking the absolute of log bias formula, and we got some of the quantities. Say, for example, the first one was associated with 0.42, the second one was associated with 0.32, and obviously this table is something that was ranked so that we have the biggest amount of absolute log bias at the top and the least amount of absolute log bias at the very bottom. And since we have all of these numbers now, we generally have a very good understanding which of these empirical covariates are causing more bias and which of these empirical covariates are essentially having causing no bias in the analysis of interest that we have. And we can simply take the first 100 or first 500 covariates, and we can then include only those top 500 empirical covariates in our analysis. But before I show you the result, I just want to make sure, what does this mean when we are selecting these empirical covariates? The basic assumption of using these empirical covariates is that we are assuming is the selected empirical covariates. So for example, the selected 500 empirical covariates that we have selected in our previous slide are collectively serving as proxies for all unmeasured confounding or residual confounding. That means that through our hdPS analysis, we are adjusting for any kind of unmeasured confounding or residual confounding. Right? So obviously, this is a strong assumption and not necessarily very verifiable in the observational data setting. But whether this idea or assumption is helpful or not, this is something that we wanted to investigate as well. So remember, when we used our kitchen sink model, including the 2400 covariates, we can see there was almost no overlap. But when we have only 500 empirical covariates, we can see, based on this analysis, there are some overlap, and we can properly do a propensity score analysis in this. So in the data analysis that we have done in our 2018 paper, this was basically a reanalysis of the Pang analysis that used a double robust method. And we essentially saw this was the crude odds ratio, which was close to 0.3. And then we just inputted 5 important covariates, and that brought our odds ratio to 0.47. And then we did our regular propensity score analysis. That means that we have included 5 important and 24 potential confounders in our analysis. In total, 29 covariates only. We had our odds ratio to 0.62. But when we included the high dimensional propensity score, when we use the 500 empirical covariates in our analysis, we see that we are getting estimates very close to 0.77. And from our previous analysis, we knew that the odds ratio was close to 0.77, and in a sensitivity analysis, the odds ratio was 0.8. And our hdPS was somewhere in between when we calculate the odds ratio using the 500 empirical covariates. So we were pretty happy about this result in this particular scenario. But we then thought about, like, is there any way we could improve this? Say, for example, one of the main criticism of high dimensional propensity score algorithm is that it is dependent on the Bross formula, and we are selecting these covariates based on the amount of bias that we got from the Bross formula, but we are doing it univariately. We are not really considering any multivariate model to select. And we know that the essential idea for hdPS algorithm is that we are trying to use the correlated information. But as you can understand, even the empirical covariates could be correlated with each other. That means that in the presence of one empirical covariate, another empirical covariate might not be useful anymore in our analysis, right? So in terms of including both of these empirical covariates that are correlated with each other, if, say, for example, if they're highly correlated, that might cause collinearity in our analysis, and we can get higher variance, right? So that could be one problem. And that was something that was discussed in this Mandaroli paper as well. And the second issue is that since we are invariantly selecting the model, we are not necessarily, invariantly selecting the empirical covariates, we cannot necessarily specify the model specification. So for example, whether there was any useful interactions and stuff like that, that we cannot do, right? So, but if we had a joint model, that would probably solve this problem. Right. So that kind of gave us some idea of thinking through the process of whether we can think about some machine learning alternative that is free from the Bross formula. All right. So at this point, we were thinking, okay, instead of going through the Bros formula, what are the other ways we can try to select the variables that are useful? And in the propensity score literature, not the high dimensional propensity score, but the propensity score literature, there are enough paper to guide us which type of variables are useful for including in the propensity score model. So for example, Bruckert, Meyer, Pearl, and Suster's paper gave us some idea about bias amplification, inflated variance, and overfitting problem in the propensity score analysis. And the gist of that is something like this, that you can have many different roles of variables, right? So for example, this is your exposure variable and this is your outcome variable. And you could have a confounder variable, and it is very good idea to include the confounder variable in the propensity score model because that will reduce bias. It is also a good idea to include the risk factor for the outcome in your propensity score model because it will reduce the variability in your propensity score model. But obviously, it is not good idea to include the instrumental variable or the variables that are highly associated with the treatment and weakly associated or not associated with the outcome. And those variables will generally induce more variability and sometimes amplify bias as well. And we do not necessarily want to include the mediating and the common effect variable or the effect of outcome variables as well. The same principle also applies for the empirical covariates for which we do not have any interpretation, right? So we generally want variables that are confounder-like and the risk factor-like. We do not want any other type of variables. And what is the one thing that is common between the confounder and a risk factor of the outcome? That both are associated with the outcome. Irrespective of whether they are associated with the treatment or not, both are associated with the outcome. But the problem is there are other covariates that have similar properties. Say, for example, the collider variables or the mediating variables or the effect of outcome variables that has the same property that those are also associated with the outcome. But remember, by design, we are only selecting the variables that or the codes that were occurring in the pre-treatment period, in the covariate assessment period that was happening before the study entry, right? So by design, we should not have any mediating variable or the collider variable or the effect of outcome variable. So if we, based on the empirical covariates that we have, if we simply try to find the variables that are associated with the outcome, that might do the trick. Even though we do not know the interpretation, but just by finding out the variables that are associated with the outcome, that might do the trick. All right, so in the machine learning literature, there are many algorithms that are helpful in selecting variables that are associated with the outcomes. So the most popular one is the lasso method that was used by Franklin in her 2015 paper. And the idea is that if the variables are collinear, it just picks one variable out of the group of collinear variable and deletes the rest. And that's how you deal with collinearity in the lasso method. But the issue is sometimes this just keeping one variable out of a group of collinear variable might be too extreme, and that gives some instability in the lasso method. And the elastic net method is something that is in between the lasso method as well as the ridge regression, and you can, there is a twinning parameter that you can choose to determine how much tuning you want to do towards that stabilization. But the problem of elastic net method is that you still need to determine the nonlinear and non-additive terms in the elastic net method, because this is essentially a parametric method where you still have to specify all of the variables and all of the model specification. In that sense, the tree-based method, say for example, the random forest method, is something that might be of some help, because they can automatically detect the nonlinearity and non-additivity. Because we are dealing with empirical covariates that are usually binary variables, that means that the non-linearity or the polynomial terms are usually not helpful, but the non-additivity or the interaction terms are generally helpful to understand which interaction terms are helpful. And this random forest method will detect those interaction terms automatically. So as an analyst, you do not necessarily need to worry about them. But the problem is random forest method does not necessarily select the most important variables. It just gives you a rank based on the variable importance plot that you can plot after the fitting the random forest model. But since you have the rank, say for example, this first variable is the most important in determining the outcome variable. So you can keep the first top 100 variables, and then you can delete the rest, similar to the high dimensional propensity score algorithm situation. So obviously there are many different algorithms that are proposed in the literature, and these methods are associated with different advantages and limitations. And you can try to use all of these algorithms to determine which covariates you find to be useful in your analysis based on their association with the outcome. So the general formulation, so there are two different formulations that we have proposed in our paper, and we have also assessed them in our paper. The first one was we just include all of the empirical covariates along with the investigator-specific covariates in our analysis, right? And then say, for example, we run an elastic net method, and elastic net method, say, for example, it gives you 100 empirical covariates in the in this lasso model. And then you select those 100 empirical covariates and you put them back in the refined propensity score model. So instead of these 2400 empirical covariates, you now have only 100 empirical covariates that are selected by the elastic net method approach. And you can do the same using the lasso method, or you can select top 100 ranked variables that were found to be most useful for the random forest approach, and you can use those variables in here to build your propensity score model, right? So that is one approach. And notice that we did not use Bros formula anywhere here. So this is a pure machine learning approach, right? All right. We did have a hybrid method where we first used the high dimensional propensity score algorithm to select the top 500 empirical covariates based on the Bros formula. And then we ran a machine learning method. So for example, it could be the elastic net method approach on those top 500 empirical covariates, as well as the investigator specified covariates. And then say, for example, out of this elastic net, we find only 100 empirical covariates that were found to be useful in predicting the outcome. And then you select those 100 empirical covariates in your analysis, similar to before, and that will give you some understanding of the refined exposure model of which variables you need to be including in the refined exposure model. And obviously, there are many other hybrid versions that are proposed in the literature. So for example, in this Levi's paper, they proposed a scenario where they applied lasso first, and then they used the high dimensional propensity score algorithm later. So the algorithm was somewhat reversed in that situation, but we did not assess that algorithm. Our algorithm was first use the Bros formula, and then we wanted to determine which of them were associated based on the lasso formula. All right, so let us try to take a look at what do the results look like. So when we use just the pure machine learning methods, and all of these methods within this green box are pure machine learning methods, you can see these estimates are not very different than what we have seen in our high dimensional propensity score estimate when we used 500 empirical covariates, right? And we also estimated the hybrid lasso and hybrid elastic net method approach, and the estimates did not vary too much, right? So in that sense, you can say all of these estimates look very close, and without knowing the true estimate, obviously this was an observational study, we did not know the true estimate, so we had no capability to judge which method is performing better or not. Also, we were using odds ratio here, which is a non-collapsible measure that makes it also harder to compare odds ratio estimates from different models. But there was one interesting finding that we found, that even though the odds ratios were very similar, but the empirical covariates chosen by different methods were not exactly the same. So only the 30% of the selected empirical covariates were common between, say, for example, the random forest and the elastic net method approach, right? So even though the selected empirical covariates were slightly different, but the results were somewhat similar. But again, like this is just one study, we cannot really do any kind of generalization. So we wanted to do some simulation. But before doing that simulation, we also wanted to check like what happens if we just rely on the 500 empirical covariates. If we do not include the investigator specified covariates. And that was because of one of the charts this Sneewi's paper showed. And this chart basically says that when you are using the investigator specified covariates as well as 500 empirical covariates selected by the hdPS algorithm, you get certain estimate. But when you are using only 500 empirical covariates without using the investigator specified covariates, you are essentially getting the same estimates, right? And this is somewhat infuriating to some of the epidemiology colleagues that I have, because like what this means is that if you fire all of the epidemiologists from your team and you just hire some of the data scientists who can run the hdPS algorithm, they will essentially come to the same conclusion as the epidemiologist from your team. So obviously for this, you need very good quality of information to have a proxy so that you can replicate the analysis result. So we wanted to check whether we can replicate this in our data sources, but we have seen that when we have used five most important covariates in our, included the five most important covariates in our analysis, the odds ratios were in between these two vertical lines. But when we deleted the five most important investigator specified covariates, but included all of the empirical covariates selected by the machine learning as well as the hybrid methods, we see the odds ratios were slightly decreased. They were still better than the propensity score estimate that we got without the empirical covariates, but they were not exactly within these two vertical lines. So obviously one finding that we have from our analysis is that the quality of proxy information matters, because we did not have many data dimensions. We were dealing with only 4 data dimensions, and that's probably why we were not able to supplement all of these proxy data, the unmeasured confounding using this proxy data information. All right, so I already talked about the need for the simulation method, and we did a plasmode simulation proposed by Jessica Franklin. And we did check a number of settings. So for example, these are the 9 settings under the unmeasured confounder setting, and we also investigated 9 additional settings under the no unmeasured confounder setting. And from all of these analyses, here are the results. So this is basically the one table that gives you the answer to the title of our talk. So in terms of the bias, so when you are using the bias criterion to check the bias-based analysis that we have been discussing in this talk, you can see sometimes the hybrid method or the hdPS methods are winning, and sometimes the machine learning methods are winning. In this particular slide, whenever you see something is bold, that means that that is a pure machine learning method. And when you are using this bias-based criterion, you can see sometimes the machine learning methods are winning and sometimes the hybrid methods are winning. But when you are using the mean squared error criterion, almost always, except for these 2 cases, the hybrid methods are winning, almost always. So even though from our empirical analysis, the results look very similar, but in terms of our simulation, in terms of the minimum mean squared error, the hybrid methods were almost always the winner. We have done some exposure-based analysis that I didn't really talk during this talk, but these are basically some a different criterion to choose the variables based on the association with the exposure, and in those category, the machine learning methods were always winning, right? But obviously, exposure-based analysis is something that is more prone to bias due to inclusion of potentially including the instrumental variables, and so I generally do not like this exposure-based analysis, but I generally prefer the bias-based analysis. All right. One thing that I should mention is that even though in terms of MSc, the hybrid methods were almost always winning, but if you look at the simulation results, and in this paper we have given a extensive list of simulation results in the web appendix. You can see all of these tables in that web appendix, and you can see the mean of the median of all of these risk differences that we have calculated. So for example, from the high dimensional propensity score, from the random forest approach, from the hybrid methods, they were very close, even though in terms of the absolute win, like in terms of MSc, the hybrid method was winning in this scenario, but all of these other scenarios, like the high dimensional propensity score algorithm and the random forest algorithm. So this is basically a random forest algorithm is basically a pure machine learning method without any involvement of the Ross formula. And that was also very similar to the hybrid method result. All right, so obviously there are some shared limitations with the high dimensional propensity score as well as this machine learning alternatives, and let me just highlight them. So the M bias and Z bias are generally the issues in the epidemiologic studies, and the way we have defined the empirical covariates and use those empirical covariates in our analysis. Our analysis is not free from bias from this M bias and Z bias, but in previous literature, say for example this Liu paper as well as this Myers paper, they showed that the net benefit of using this high dimensional propensity score algorithm or the empirical covariates can still be beneficial. So some other limitations are that empirical covariates do not necessarily have an interpretation in the particular research that we are conducting. But then again, empirical covariates are only used in the propensity score algorithm, and we generally do not interpret the coefficients from the propensity score model, right? So here, even though they do not have any interpretation, but no interpretation is needed, to be honest. And we have to understand that the sole purpose of doing the high dimensional propensity score algorithm is that we are trying to address the residual confounding, right? Say, for example, some people try to make this case that propensity score algorithm is the base case and high dimensional propensity score algorithm is basically an extension. But generally speaking, propensity score algorithm has a very unique situation because it has some good statistical properties, and we exactly know what those properties are. But it requires, propensity score algorithm requires that all variables are measured. But for high dimensional propensity score or the machine learning alternatives, we begin with the assumption that there are some unmeasured confounding going on, and residual confounding adjustment is the main purpose. So to begin with, the aims are slightly different, and I generally do not think that those are equivalent, to be honest. And also, from a very purist view, from a theoretical perspective, there is no separation of design and analysis stage in the bias-based analysis. What that means is that, say, for example, in the Ross formula, we are trying to see the association between an empirical covariates with an outcome. And we are doing the same with the machine learning methods. We are trying to select empirical covariates based on the association with the outcome. That means that we are selecting the variables by looking at the outcome. But in the propensity score algorithm, generally it is suggested to not look at the outcome data to select the covariates, but essentially we are violating that principle. So this is one problem, and obviously we are doing variable selection, so we can be subject to the post-selection bias, and that is an active area of research. But there are some additional advantage and limitation of this these machine learning methods that we were using in this paper, and that is say for example, when we are using the lasso method, we can determine an automatic cutoff because lasso will give you certain number of covariates, right? So you do not need to determine 100 or 500 or anything like that. Lasso will determine how many covariates are useful. And also, say for example, even though lasso method is useful in determining a subset, it might not give you a direct understanding of the ranking. So for getting a ranking, you have to go through the variable importance plot, and that will give you the idea of ranking. But the greatest advantage of this method is that you do not have to be restricted to binary confounder, exposure, and outcome. Using the pure machine learning method, you can deal with any type of variables you want. But there are some limitations of the work that I have done. Like there was no coverage that was assessed in that paper, and that was a something that could be done and may be done in the future. And we have only considered a few machine learning algorithms that are popular. There are many machine learning methods that can be helpful in variable selection, and those could be used as well. We did not also use the double robust methods in our analysis, right? All right, so going back to the motivational example that we have started with at the very beginning. So this is the paper by Dr. Basham, where he used the propensity score method at first, then he used the high dimensional propensity score, and then he used the machine learning version of the high dimensional propensity score, and all of these estimates were very similar. So basically, we were concerned that not including the smoking was biasing our analysis, but then we included the most important empirical covariates, and we saw the results did not really budge that much, right? So generally speaking, this is the format that I prefer in a subject area paper, where we do the propensity score analysis first, and then we do the high dimensional propensity score analysis to just check how much of an adjustment we are making just by including the empirical covariates. So the high dimensional propensity score or the machine learning methods are generally the secondary method, and the propensity score method is generally the primary method. But obviously, in a methods paper, you can certainly use high dimensional propensity score algorithm as your main or primary analysis. So one example of the use of high dimensional propensity score as the main analysis is this Brown paper from JAMA from 2017, where they have used many different analyses, but they picked the high dimensional propensity score algorithm where they have used the inverse probability weighting approach, and the hazard ratio was 1.61. But since this confidence interval was including 1, and there was like these 3 decimal points included here, they have decided that there was no association, and this created some outrage among the statistician, and there are some of the like this is one of the paper that discussed the issue in detail. The problem was not in methods, by the way. The problem was in the interpretation. So obviously, we can, as methodologists, we can develop many interesting methods, but we have to be also careful, like when those methods are used and interpreted in the research, like how the researchers are essentially interpreting the results, right? Okay. I know that I'm almost out of time. I just want to spend a couple of minutes to talk about some of the research directions that and some of the papers that came out after at the same time of our paper, because that paper came out like almost 4 years ago. So last year there was a very interesting paper that used the autoencoder to reduce the dimensions of the empirical covariates, and you can see in this article, they suggested that the autoencoders are very useful in high dimensional propensity score algorithm, and autoencoders are basically a artificial intelligence version of the principal component analysis, right? And they showed that this is useful, but it was more useful in the shallow learning when there were less layers, right? And the most important finding that I found to be useful is that it did not perform better than lasso in terms of multiple metrics, right? So You can use very powerful machine learning methods, but you have to be very careful about some of the statistical property that it brings. There was a TMLE version that was proposed, and there is a group importance score that was also proposed from the same team. And that's not published, that's in the archive yet. And there are some other directions that where epidemiologists are going in recent years. So for example, NIME proposed this sample splitting that should be used in machine learning algorithms. I think this is a very good idea, and this could be one dimension where the machine learning people, who are interested in empirical correlates could be using. There are other papers such as this Zivik paper that proposed this cross-fitting algorithm. This is basically a algorithm similar to cross-validation, but this has a different organizational layer, and this shows some good properties, statistical properties, if you use them in your analysis when you are using non-parametric or machine learning methods. And other two papers that I found to be useful was the Balzer paper as well as the main paper that showed the importance of choosing the superlearner library judiciously. And you can have access to the slides and you can take a look at these papers later carefully, but I generally thought that these are useful papers in our that are related to our 2018 paper. All right, so the take-home message, this is the last slide. Is that the high dimensional propensity score and the machine learning alternatives generally reduce the residual confounding. With the aesthetic mark is that you have to have good proxies available. And high dimensional propensity score algorithm is dependent on the Bros formula, but when you are using the machine learning methods, you do not need to be restricted to the Bros formula. That means that you can use other variables that are non-binary, right? And in our analysis, we found the hybrid methods to perform better. So obviously, pure machine learning or the pure hdPS, none of them were always good, but hybrid method was performing better almost in most of the scenarios. And this is an active area of research, so research is not done. I hope to see more and more research in this direction in the future. And thank you.
Great, thank you, Ehsan, for this very comprehensive overview of your work, along with the relevant lines of research. I think this is extremely relevant and important for all of us. So really appreciate you covering this in depth. So I think we have one question in the chat box, which is related to your slide 24, where the question is, if you can describe what should be done and why for inclusion of confounder proxies on your slide 24, and just a general question about your paper, whether you included propensity score trimming or not.
Okay, just to remind the readers, this was the slide 24. Can you describe what should be done and why for inclusion of confounder proxies? So inclusion of confounder proxies is not necessarily a new idea. This is like in the epidemiologic principles, we have always knew that proxies could reduce the amount of unmeasured confounding, but with the caveat is that sometimes the direction is not clear, like in whether it is going in the right direction or in the left direction, it's not necessarily clear. So we have to be a bit careful about incorporating proxy. And that is why I suggested that maybe we should use the propensity score analysis first, and then we should use all of these proxy adjustment method later, so that we can understand which direction our adjustment is going. And the second question was more about the trimming method. Generally speaking, sometimes this is an ad hoc method that people generally use when there are extreme weights or the extreme propensity scores in the analysis. But obviously, there are some theoretical implications of using these ad hoc methods. So for example, sometimes even though you are reducing the mean squared error, but maybe at the expense of bias. And again, I generally prefer to conduct the analysis with the original propensity scores first, and then do another sensitivity analysis after trimming, and that might give you a good understanding of where your estimates are going in general.
Okay, great. Thank you for covering those questions. So we don't have any other questions in the chat box, but people can feel free to write one. I have one quick question on your machine learning based approaches. So you model an outcome conditional on many covariates using these machine learning based models or methods. So one of the considerations there that is really important for a lot of the work that we do in Sentinel is around rare outcome situations. So we are many times in a setting where a drug is new, you don't have many exposed people to begin with, and then you have even fewer people with a rare outcome of interest. So my question is twofold. So first, what was the prevalence of the outcome in your examples? Did you vary that? And then the second is, do you think that there is any potential for model overfitting if you are faced, if with the machine learning approaches, if you are faced in a rare outcome situations?
Right. So with respect to your first point, if the outcome is rare, obviously that is one disadvantage for these machine learning methods because we are relying on the outcome and the outcome is rare. So the model will probably be more unstable in that scenario. In terms of solution for that, I do not necessarily have a direct solution. Maybe we need to look for some machine learning methods that can better deal with rare outcomes, and maybe we can resort to those. In terms of the overfitting problem, obviously, as you have seen in the one of the autoencoder paper that I just showed, that overfitting was essentially a problem. Mm-hmm. And when they did deep learning with 7 hidden layers, that created more MSE, and when they did shallow learning, that was slightly better in the sense. So overfitting is a problem that is obviously going to be the case for any kind of a model that are associated with high predictive ability. And in that situation, I think some of the cross-validation or the cross-fitting algorithms that are being proposed in the newer literature that I have showed in some of these slides at the very end, I think those can be a great solution to some of these overfitting problems that we can have by including all of these too many covariates in our analysis.
Thank you. I think there is one question that just came in. I think it's a follow-up by Hayden Smith. For variable selection, is it just predictions? Any thoughts on including child and sibling nodes? I think it's still related to your slide 24.
Yes, I think so. For the machine learning methods that I have described in my 2018 paper and some of the other alternatives that I have seen in the literature in terms of the high dimensional propensity score, most of these algorithms are basically relying on the predictive ability of the outcome. So like not any kind of causal thinking, because we know that these are proxy variables and we do not necessarily have direct interpretation. If this was an investigator specified covariate, then we can be more judicious in thinking whether we need to include this or not. But since we are dealing with proxy variables, we are basically relying on the predictive ability of the outcome in that machine learning method.
Okay, great. And I guess we have 1 minute left, so I will ask one more question. Something you said really resonated with me, and I think it's something that gets lost when we use these empirical based confounding adjustment, which is the outcome blinding principle. And so you covered that nicely why this may be problematic. So I wanted to ask you if you still think it's problematic if we are really not trying to make any interpretations or even reviewing the outputs except for the final adjustment that you do when using these machine learning based approaches to do confounding adjustment or select your variables. So what's the general consensus around that in the field in your opinion?
So my understanding that you are generally asking when we are using these machine learning methods with this many different proxy variables. These are basically empirical solutions to a practical problem. And obviously, we do not have a good theoretical foundation to include these variables because we do not necessarily have a good theory why we're including this particular empirical covariate. But essentially, we are relying on using the correlation between these variables because these variables are essentially coming from the same patients. So we are hoping that those would be informative in letting us know how this particular patient is doing in terms of the health outcome and stuff like that. So I do agree that there is no perfect solution. Like you can always take a purist view that you should not include these variables because these are kind of ad hoc approaches. But then again, like as we have seen in multiple simulations, including mine, that these proxy adjustments really work. So I do feel like we have some theoretical basis, of course, for some of these methods, but some of these ad hoc methods that we are using, in reality, they show that they are useful. But we have to be always careful about the interpretation. That I agree totally.
Right, and using outcome information to generate your models is, of course, is an issue as well, which is what you can avoid if you're using just traditional propensity-based approaches.
Yes.
Okay, excellent. So this was really, really comprehensive and excellent presentation. Thank you, Ehsan, and I thank everybody for joining today, taking the time. Just as a quick reminder, we will be posting this recording as well as the slides, and I will see you all next time. Thank you, everybody, and thanks, Ehsan, especially.
Thank you.